Hello everyone, Sonfam here. Welcome to another video of LeetCode Contest Solution Walkthrough. This is bi-weekly contest 128. And today we are going to tackle the hard problem of this contest, which is find the number of subarrays where boundary elements are maximum. So the description is you're given an array of positive integers nums. You have to return the number of subarrays of nums where the first and the last elements of the subarray are equal to the largest element in the subarray. So you can see here that there are actually two conditions. The first and last is the same, and the first and last are equal to the largest element in the subarray. As an example, you have 1, 4, 3, 3, 2. Here, the output is 6. And the reason for that is that for any subarray that has only one element, so you can see here 1, 4, 3, 3, 2, they all count, right? Because in an array with one element, the largest element is that element, and the first and the last element is also that one. So we all count them here. Now, an interesting subarray is 3, 3, because the first and the last elements are the same, and the largest element is also 3. One interesting thing about this example is that it can be a little bit misleading in terms of tricking people into doing this same number counting and then calculate the number of subarrays because there's only example of elements are the same within an array. However, you can also have something like 30, 15, and 30, right? Which is one of the tests that I initially failed in the contest. Notice that they should count as well, right? Because the first element is 30, the last element is 30, and the largest of them is also 30. So this one should also count here. Let's go to the constraint of the problem. So the number of elements in the array is between 1 and 10 to the fifth. So usually what this means is that you have to come up with an O of n or n log n solution, meaning that you only visit each element once somehow, or come up with a way to divide the problem in half somehow, right? And the reason for that is that, like, if your algorithm is only n squared, then this 10 to the fifth will become 10 to the 10th. And usually when your time complexity is this way, it is a sign that it will time out when it actually runs the test case when the length is extremely long. So we definitely want to avoid that, keep that in mind, and come up with some kind of O of n or n log n solution. The other constraint is that the value of each number is between 1 and 10 to the ninth. I think usually this just means that the value doesn't matter much. And then because it's so big, you should not count on any kind of counting incremental because 10 to the ninth incrementation would also be too long for our problem. So notice here that we have to come up with an O of n solution. You might have also noticed that we somehow need to keep track of the numbers that we have so far. Actually, let's go through an example. Right. Um, if a solution is O of n, then we have to walk through each element, right? And I think one really helpful way to think about this problem is what kind of information you have to keep track as you walk through the array in order to solve the problem, right? So let's walk through them one by one. So first of all, you have a 1 here. And then when you encounter number 1, then yeah, you count them as 1, right? There is one subarray that qualifies here. When you go to 4, 4 also counts. But what do we do with number 1? We probably want to ignore number 1, right? Because once there is an element that is already larger than this element, then we don't really care about them anymore because there is no subarray that from 1 that goes over 4 that can actually form a subarray that qualifies because there's already a bigger number here. So here we can ignore number 1. Now we go to 3. 3 is a subarray by itself. 3 is smaller than 4, so if you do a subarray of 4 and 3, it will not qualify because the first and last number is not the same. However, notice here that because 3 is smaller than 4, there can still be a potential of a number 4 in the future. So we should still keep track of this number 4 in our system some way, somehow. At this point, I think you probably need to come up with a data structure in mind. What kind of data structure that would allow us to sort of keep track of certain kind of numbers based on certain conditions? Okay, let's keep going. We have another number 3 here. This number 3 also count on its own and qualify. Now, when we connect it with this 3, it should also qualify as well. So this number 3 should count as 2, right? Because it actually can form with itself and one of the array that begins with 3 in the past. Now we encounter number 2 here. Number 2 is a subarray that qualifies on its own, so we put a 1. And we don't want to remove the tracking of these to number 3 here because there can still be another element in the future after 2 that is equaling to 3 and should potentially form qualifying subarrays with these previous members. Now let's go to this 3. This 3 is very interesting. Notice that for this 3, we should remove the tracking of 2 because we no longer need to care about number 2 anymore. There are no subarrays that goes from 2 to any elements passing 3 that would qualify. But we want to connect these 3 to these previous 2. Notice here that we have number 3 on its own as a subarray, 3 to this one, so 3 to 3 also qualify subarray, and 3 to this one also qualify as array. So we want to count 3 here. And now we encounter number 4. So this number 4, notice that we don't have to care about all this tracking of 3 anymore, right? All the previous 3 we can ignore because now we actually have a number that is bigger than 3 now. But 4 should still connect to this one. So it should form 2 subarrays here because 4 can form on its own, and 4 can also form with a previous 4. If I describe it this way, what data structure do you think that would help us best perform this kind of tracking? And if your answer is a stack, then you would be very much correct here. We need to do the we need to do the stack because it has a lot of quality that we want to do. One is that we keep adding the number and sort of stacking them, the smaller that we encounter it. And when we want to remove the number, we also want to remove from the smallest to the biggest, right? So a stack would very much do the job for us here. Just as a simulation, so initially the stack will have number 1. And then when we go to 4, we will remove all the number in the stack that is smaller than 4. And then we add 4 here. I think something is happening with my okay, let's just kind of draw it outside this way. We have a number 4 here, right? Now we have number 3. We also do a 3 here. And now we encounter 3. Notice that if we try to remove all the numbers that are smaller than 3, we still keep track of the 4. So this is one of the nice things about using stack is that it's a very natural solution to our algorithm. What do we have to keep track when we try to add each number here? The thing that we will keep track is that how many times this number has appeared so far. Here, when we add number 4 to the stack, we will put a 1 here. When we add this 3, we will put a 3. We put a 1 here, which is the counting, the one number 3 that happened so far. When we encounter the second 3, we notice that this value is equaling. Once we remove any number that is smaller than 3, the value that remains has to be either smaller or equaling to 3. So when that is the case, right, we simply just need to check, compare the value with the top of the stack. And then if they are equaling to each other, we can increment this 1 to 2. And notice that when we increment the 1 to 2, this also happens to be the number of qualifying subarrays at this position as well, right? Because you can form a good subarray from that number with any of the number in the past, including itself. And because we already remove all the elements in the stack that are smaller, we also guarantee that anything in between the stack must be smaller as well, right? So there's no worrying that there could be a bigger elements here because they would have been removed already when we encounter that elements, right? Now the next one is 2. We'll have 2 of 1 here. And then we encounter 3 again. Now 3 is bigger than 2, so we should remove this item from the stack, right? Now we have 3, so we increment 3, and then we add 3 here. And now we encounter 4. We have to remove the top of the stack, which is 3, because 3 is smaller than 4 now. We don't want to track these 3s anymore. But 4, there was one number of 4 that happens in the past in which it has not been overtaken by any element yet. So we increment 2, and then we add 2. Notice here that let's just assume that there is another number 3. This number 3 will restart the count again to 1 because we don't want to count these 3, right? If we count these 3, it has to pass number 4. And if we pass number 4, then that is no longer a qualifying subarray anymore because it's no longer the largest element. As you try to increment and keep track, you simply just need to add what is the number that is being tracked, what is the number of element incrementation that appears in the stack so far. In that way, you simply add these counts. So 1, 1, 1, 2, 1, 3, 2, 3. If we add them together, then that would be 14 for this problem. So yeah, that is the overview of what the solution would look like. I think once we realize that it should be a stack, it is a decently simple and straightforward implementation of the problem. It's not very hard at all. You simply just need a stack that keep tracks of the element that we are tracking and also the count, the number of times that they have appeared in the past. Okay, so let's go to the coding of this problem. I'll sort of go a little bit bigger here. So you can see that I start with a stack. And I find it very useful that every coder should probably have a comment defining what each stack should contain, because it actually helps a lot in the future when you try to pop things or push things into it, making sure that it's very, very consistent. So in this case, I have the value of the number itself and the number of times that it is appearing in the past, that it doesn't pass any bigger numbers. I have a return, and then I go through each element. Notice here that when I go through each element, I constantly check the top of the stack, right? If there is any element that is smaller, I pop them because I don't have to track them anymore. And I keep doing so until I found the number that is equal or smaller than the top of the stack, in which case I will break. Now, if there is no element in the stack, which means that this is just like the highest number so far, we simply append them and then also increment the count that is 1. If they have appeared before, right, because we already performed this stack removal, we guarantee that, hey, any numbers that uh, any numbers that is in between this one and all the previous time that this appears in the past must be smaller, right? So we simply increment the count and then add it to the return. And then if it is smaller than the top of the stack, then we simply make a new entry, and then add 1 to the return. And then we return the solutions. And then if you run this solution, you will see that it is the correct solution here. So yeah, I think this problem is actually one of the simpler problem for a LeetCode weekly contest. You can see here that the implementation itself is not very long at all. I think the most important thing about this problem was that you read the description of the problem carefully, think about what kind of data structure, what kind of information it should hold, and then what kind of infrastructure that should satisfy. Once you do that, then the realization that the stack is a solution should be very straightforward, and the implementation of the solution is also straightforward as well. All right, that's it for today. Good luck doing this problem, and I'll see you on the next one. Goodbye.